Hello and welcome to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering education. Today in our playlist class 12th physics, in the unit of electrostatics, we will discuss superposition theorem for electric field intensities and we will solve some classical textbook problems to understand vector summation of electric field intensities when several charges are contributing electric fields, and we will handle equilateral triangle configuration and square configuration and understand how present day competition examination questions can be simplified using these techniques. Let's start. Two charges Q and minus Q of equal magnitude and opposite polarity are placed at two vertices A and B of equilateral triangle ABC. We have to find out electric field intensity at the third vertex C, center of this equilateral triangle O, center of this side AB where two charges are placed O dash, and center of this opposite side AC, and point is O double dash. At third vertex, two charges of equal magnitude and having same distance position of observation point produce equal magnitude electric field. Positive charge Q of position A produce electric field EA on joining line outward, and negative charge minus Q at position B produce electric field EB on joining line inward as shown here, and both charge magnitude and distance of observation point from charge is the same. So electric field magnitude of charge A at position C and charge of position B at point C is the same, and it is given by KQ upon A square. Q is charge magnitude and A is distance of observation point. Now this inner angle of equilateral triangle is 60, so this outer angle is 120. Two equal magnitude at an angle 120 will produce resultant electric field just midway parallel to this AB line. The resultant electric field is EAB, and for 120 angle the resultant got same magnitude as equal individual vector components. So resultant electric field is KQ upon A square, and it is directed in EAB direction parallel to AB line as shown here. For this triangle center position O, electric field contribution of positive Q charge placed at A is on joining line outward EA, and similarly for negative Q charge positioned at B, electric field contribution at center point O is on joining line but inward EB as shown here. Now the distance of observation position from both charge and the magnitude of both charge is the same, so electric contributions are equal in magnitude. This angle between equal magnitude of two electric field intensity E and EB is 60 degree. To find out magnitude of EA and EB, we have to find out distance of center point O from vertices A or from vertices B, and AO and BO is equal in magnitude, and let this distance is x. Now this x distance is BO is 2/3 of BO dash, which is a perpendicular bisector on AC side, and if this AB dimension is A and this angle is 30, then BO dash is A cos 30, and this center divide this length in 2:1 ratio, so it is 2/3 of total length, and cos 30 is √3/2. Simplification will result this distance as A by √3, and if for Q charge distance is taken as A by √3, then electric field intensity as inverse square of distance becomes 3 KQ upon A square. Both magnitudes are equal, angle is 60 degree, so resultant is midway EAB, and it is √3 times of single individual 3√3 KQ upon A square. This configuration of equal magnitude and opposite polarity charge is known as electric dipole, and for this dipole at mid positions the distance from each charge is A by 2 and electric contribution is KQ divided by A by 2 whole square or 4 KQ upon A square, and both electric field contribution of positive charge joining line outward and for negative charge joining line and inward are in the same direction, equal in magnitude, so the addition of the two will give me resultant electric field 8 KQ upon A square. For center point of side AC, that is O double dash, two charges, one of position A plus Q at a distance A by 2 produce electric field EA, and magnitude of EA is KQ divided by A by 2 whole square or 4 KQ upon A square. And for negative Q charge placed at position B, electric field contribution need this distance BO double dash, and BO double dash distance is A cos 30. This angle is 30, so this is A cos 30, and cos 30 is root 3 by 2. And at root 3 A by 2 distance from minus Q charge, electric field is inward directed towards negative charge, and it is 4 by 3 times KQ upon A square. Now these two electric field as directed here, EA and EB, are at 90 degree, and the resultant can be obtained by simple Pythagoras calculation. And Pythagoras results say that resultant electric field is square of first contribution and square of second contribution. First contribution is 4 times of KQ upon A square, and second contribution is 4 by 3 times KQ upon A square. KQ upon A square is kept common, and this square root calculation is performed by again taking 4 as common, and 1 square is 1, 1 by 3 square is 1 by 9. When we take 9 as an LCM, it becomes 10 by 9, and square rooting will result as 4 root 10 by 3 KQ upon A square. Let's take another simple calculation on superposition. We have given a square, and on 4 vertices of it, charge plus Q plus 2Q minus 2Q and plus 2Q are placed, and we have to find out resultant electric field at the center of this square, and it is given that center point got at distance D from any vertices. Since electric field intensity is a vector quantity, so for superposition calculation, direction first rule is important, and electric field of this positive Q charge EA is on joining line outward, of B again a positive charge on joining line outward. For C, which is a negative charge, it is on joining line inward, and for D, which is positive charge, electric field is on joining line outward. So these EA, EB, EC and ED are respectively electric field direction of 4 charges. The resultant electric field is vector summation of these 4 individual contributions. Now here it is easy to consider electric effect of opposite vertices of square like A and C and B and D, and we found that electric field contribution of B and D are opposite, and A and C are in the same direction, so they will get just added up and they will be straightforward subtracted. Since electric field contribution of this plus 2Q charge and this plus 2Q charge with the same distance is in the amount same, it is K 2Q charge and distance D inverse square equal and opposite, so EB and ED result will become 0. Similarly, electric contribution of E and EC in the same direction will added up to give me resultant electric field. So resultant electric field is simple summation of electric field contribution of A position charge at D distance and C position magnitude 2Q at D distance, and resultant is 3KQ upon A square directed in A to C direction at point O. Let's take a very important and informative textbook problem. For a square at all vertices identical amount of charge are placed, and we have to find out a suitable center charge amount which will produce equilibrium of this 5 charge configuration. For equilateral configuration, identical amount of charge, then at this symmetrical center position, resultant electric field is always 0. So charge of any amount placed at O remains always in equilibrium. Let's calculate equilibrium condition for charge of position D. So for this charge of A position make a repulsive force Fa, and similarly repulsive force of charge of position B and C is FB and FC on joining line outward as shown here. For square of side A, electric force of 2Q charge at a distance A is KQ square upon A square. So force of B charge and force of C charge on this charge of D position is KQ upon D square. Let's call this force as F. Now position D and vertex A got a distance root 2A, and force of A on this Q charge is KQ square upon root 2A whole square, and it is F by 2, half of other two forces. Now if we see these 3 forces FA, FB and FC, it is easy to find out resultant of FC and FA, which is equal of magnitude and having 90 degree angle. So resultant is root 2 times and midway, so it is root 2F resultant of force B and C, and this resultant is in the same direction as of force of A position. So the total force of A, B and C Q charges is summation, and this summation is 2 root 2 plus 1 by 2 KQ square upon A square. Now to produce similar amount of force, opposite will make equilibrium condition for this Q charge, and this could be produced by a negative Q charge placed at center position, because negative charge will attract this positive Q charge, and if the two forces are equal and this center to vertex distance is A by root 2, so equality will results in K small q and A square will get cancel out, and this square become 2 at numerator, and when we side change it goes to denominator side, and 2 multiplied by 2 become 4, and capital Q got this magnitude. If we place such magnitude at center, all 5 charges remains in equilibrium, and if center charge got a magnitude higher than this, then all 4 charges will come to this central charge position, and this center charge position will remain at center position. And if this magnitude is smaller than this magnitude, then this will remain here it is, and these 4 charges, if left free, will go to infinity. Let's take another problem. 3 identical Q charges are placed at 3 vertices of an equilateral triangle. What is resultant electric field at any vertex by this configuration, and what is the resultant force on that charge? We have to calculate. And what should be a suitable value of negative charge at center position so that this system of 4 charge symmetrical configuration remains in equilibrium. For electric field intensity calculation at vertices C, the charge placed at this position is treated as test charge, and its own contribution in electric field is considered at 0. So 2 charges of vertex A and B produce electric field on joining line outward EA and EB as shown here, and Q charge at a distance A has produced electric field KQ upon A square. 2 electric contributions are equal in magnitude and got 60-degree angle between them. Then the resultant of these two is midway and root 3 times of 1. So resultant electric field at position C is root 3 times KQ upon A square. Now in this electric field, when we place this Q charge of vertex C, that charge would have a force QE equal to root 3 times KQ square upon A square. For equilibrium condition of this charge Q placed at position C, we have to produce resultant electric field 0. So an additional electric field by this center charge is required, which is equal and opposite to this EAB electric field, so that resultant electric field of position C becomes 0 and force on this charge becomes 0. So 2 charges of vertex A and B has produced an electric field root 3 times KQ upon A square at position C, which has produced a force on C charge root 3 KQ square upon A square. And for equilibrium of this charge, we need another electric field by this negative Q charge equal and opposite to this EAB electric field, and that electric field is EQ. And for EQ calculation, we need distance of vertex C from center CO. CO distance is 2/3 of CO dash, and CO dash is A cos 30, and calculation will result as A by root 3. So this Q charge at A by root 3 distance produce an electric field magnitude which is equal and opposite to EAB electric field, and EAB electric field is root 3 KQ upon A square, and equality relation will fetch us a result of capital Q magnitude as Q by root 3, and it should have a negative polarity. We hope that practice of these classical textbook problems will definitely enhance your competency and understanding about superposition of electric field intensities, and now you can solve similar type of other questions with quite ease and convenience with confidence. If you like this study material, do share it with your friends, and you can also join membership of our YouTube channel for study material and online classes support. Wishing you a great success in all competitive examinations. Thank you very much.